Alright guys, going ahead and starting our review here with number 2. It says convert the pressure from 3.4 atmospheres to millimeters of mercury. Now, the conversion factor that we're going to use is 1 atmosphere equals 760 millimeters of mercury. Okay? Now you can find this conversion factor on your formula chart. So all we do now is we just start with the number it gives us, 3.4 atmospheres. Okay? And since atmospheres is on the top, we put atmospheres on the bottom. So we put 1 ATM right here. And we put our 760 on the top, because that's what we're converting to. And then we go 3.4 times 760, and that will give us an answer in millimeters of mercury of right around 2,584 millimeters of mercury. Alright, moving on to number 4. Now in number 4 it says a certain quality of gas is a volume, so it gives a volume in liters, at a temperature, which is already in Kelvin, and it says at what temperature, so we're searching for T2, would this quality of gas be reduced to, and it gives us another volume. And it wants us to answer in units of Celsius. So we're setting this up, we write down what we have. We have a V1, which is 0.84 liters. We have a temperature, or a T1, of 298 Kelvin. We're searching for T2, so we're trying to figure out what is T2, and we have a V2 of 0.62 liters. Now, the equation that we're going to be using for this is our Charles's law, which is V1 all over T1 equals V2 all over T2. Now from here, remember, if we see a fraction, we always cross multiply. So we have V1 times T2 equals V2 times T1. Now if we look at what we're solving for T2. So this is what we're solving for. We divide by what's next to it. So we divide by V1. So in our equation, it'll be set up where we have T2 equals our V2, which is 0.62 liters, times our T1, which is 298 Kelvin, all divided by our V1, which is 0.84 liters. Okay? Then, from here, all we end up doing is we divide this out, and we'll get a T2. We get it in our calculator, and then we just subtract 273 to get it back into degrees Celsius. Alright guys, moving on to number 6. It says an aerosol can contains gas under a pressure, and it gives us a pressure at a temperature of 19 degrees Celsius. If the can is left on a hot sandy beach, the pressure of the gas increases to 4.71 atmospheres. What is the Celsius thermometer or Celsius temperature on the beach? So we're trying to find our T2. So we first have to write down what we're given. We're given a pressure 1 of 4.5 atmospheres. We're giving a temperature 1 of 19 degrees Celsius, which we know that we have to add 273 because we can only do our math in Kelvin, which we add 273 to it, and we get 292 Kelvin. Okay, and then we have our P2, our second pressure, of 4.71 atmospheres. Okay, so the only thing that we're given are pressures and temperatures, so we're going to be using Gay-Lussac's equation, which is P1 all over T1 equals P2 over T2. Now remember, whenever we see this, we always cross multiply, so we get P2 T1 equals P1 T2, which we know that we're solving for the second temperature, so we divide by what's by it. We divide by P1. So when we set this up in our problem, we see that we have T2 equaling our pressure number 2, which is 4.71 atmospheres, times our temperature 1, which is 292 Kelvin, all divided by our first pressure, which is 4.5 atmospheres. When we do this, we get a T2 temperature of 305.63 Kelvin. To get it into Celsius, because this problem wants to answer in units of Celsius, we then just subtract 273 to get it back into degrees Celsius, which our answer for this problem should be 32.63 degrees Celsius. All right, moving on to number 8. It says 3 of the primary components of air are carbon dioxide, nitrogen, and oxygen. In a sample containing a mixture of only these gases at exactly 1 atmosphere of pressure, the partial pressures of carbon dioxide and nitrogen are given, and they give us both the partial pressures here, and it asks us to find what is the partial pressure of oxygen. Okay, so basically by saying all 3 gases have a total pressure of 1 atmosphere. Now we see that these units are torrs. So I know the conversion factor that 1 atmosphere equals 760 torrs. Okay, we know that. So we know that our total pressure, our PT, is going to equal 760 torr. And these are our partial pressures. Anytime you are solving for partial pressure, you always subtract. So what we should get from this is we should have our partial pressure of oxygen gas equals our total pressure minus our 2 partial pressures. And that will give us the partial pressure of oxygen gas, which is right around 191.556 torrs. Okay, moving on to number 10. Now, number 10, it says, assuming all volume measurements are made at exactly the same temperature and pressure, what volume of hydrogen gas, so we're looking for the volume of hydrogen gas, is needed to react completely with, and it gives us 2.5 liters of oxygen to produce water vapor. Now, we're looking at this, and it tells us our equation that we have. We have hydrogen gas, which is represented as H2 because this is diatomic, so we put a 2 there. We have oxygen, that's what it's reacting with, and it's O2 because it's a diatomic as well, and it produces H2O. Okay, this is our equation. Our next step is we're doing stoichiometry here, so we have to have a balanced chemical equation. So I have 2 oxygens, so I put a 2 right here. Now I have 2 oxygens and 4 hydrogens, so to balance it out, I put a 2 right there, and I'm balanced. Now, I'm dealing within the problem. It wants to know the volume of hydrogen, so I know I'm dealing with that. And it gives us 2.58 liters of oxygen. Now, because they're at the same temperature and pressure, we know that this mole ratio can be said that it is a liter ratio now. So 2 liters of hydrogen equals 1 liter of oxygen. So all we do is we set it up. We have 2.58 liters of O2, and this is our conversion factor. 1 liter of O2 goes on the bottom, and 2 liters of hydrogen goes on top. And that's all we have to do to convert it to liters of hydrogen. And then we just multiply here, multiply the top, divide by 1, and we see that we get an answer of 5.16 liters of hydrogen gas. Now, moving on to number 12. In number 12, it says, what is the volume of 0.150 grams of C2H2F4 vapor at 0.579 atmospheres and 42 degrees Celsius? So we look at what it gives us. It gives us an atmospheres, it gives us a temperature, it gives us a mass, and it gives us a formula. Okay? Now, because it only gave us one set, meaning it only gave us one pressure, it only gave us one temperature, it didn't give us more than one of those values, we know that we're going to be using Pivner, the ideal gas law, PV equals nRT. When we're using this equation, our pressure will have to always be in atmospheres, our volume will always have to be in liters, N will always have to be in moles, and T will always have to be in Kelvin. Okay, so we look at what we're given. Okay, we're given a pressure, and that's good because it's given in atmospheres, of 0.579 atmospheres. It gives us a temperature, It's not in Kelvin, but we can convert it to Kelvin by just adding 273 to it, and we get a Kelvin temperature of 315 Kelvin. We need moles because we're solving for volume, so we look at this and we see that we have a mass. Now, moles, or N, always equals our mass, which we have of 0.150 grams, divided by our molar mass. So we have to find the molar mass of C2H2F4. So we have carbon, hydrogen, and fluorine. Okay? We have 2 carbons, 2 hydrogens, and 4 fluorines. We multiply them by their masses on the periodic table, 12.01, 1.01, and we see that we have 14.01. Okay? We multiply them and add them together, and we get a molar mass of 102 grams of the molar mass. So we take this and we divide it by 102 grams, and we get an N value, or a mole value, of 0.00147 moles. So now we have N. Okay? So we're solving for volume, and we look at R. Now, R is our ideal gas law constant. We always have R. It's 0.0821, and it never changes. We always have that. Okay, so all we end up doing is plugging everything in. We're solving for volume, so I'm going to have an equation where I have volume and divide by pressure on both sides. It cancels, and we have volume equals our moles times our ideal gas law constant times temperature divided by pressure. So we go ahead and we plug all this in. Volume equals our moles of 0.00147 times our ideal gas law constant, 0.0821, times our temperature of 315, all divided by our pressure, which is 0.579 atmospheres, and we get a volume in liters of right around 0.06568 liters. Okay, moving on to number 14. It says a sample of nitrogen gas is contained in a piston with a free-moving cylinder. At 0 degrees Celsius, and the volume of the gas is 387 milliliters. To what temperature must the gas be heated up to occupy 479 milliliters? So we see that it's given us 2 volumes and 1 temperature. So we're dealing with volume and temperature. That means we're going to be using V1 all over T1 equals V2 all over T2. Remember, we cross multiply and we get V1 T2 equals V2 T1. Okay, and it wants to know to what temperature. So I am solving for my T2, so I divide both sides by V1, and they cancel out, and I get T2 equals this. So all I have to do is plug in what I have. I know that this is my first volume, so it's V1. This is my first temperature, so it's T1, and this is my second volume, so it's V2. Now, one thing with the temperature, remember, it has to be in Kelvin, so we add 273 to it, which 0 plus 273 is just 273. So we get T2, which equals our V2, which is 479 milliliters, times our T1, which is 273 Kelvin, divided by our V1, which is 387 milliliters, and we see that we get a T2 temperature of right around 337.89. Now remember, it wants it in units of Celsius, so after we get done, we go ahead and subtract 273 Kelvin from it to get it back into Celsius, and we get an answer of right around 64.8992 degrees Celsius. Alright guys, moving on to number 16. It says a gas sample occupies 4.8 liters at 23 degrees Celsius. What is the pressure given that there are 1.0 moles of the gas sample? Now it doesn't give us two temperatures or two pressures, so we're dealing with PV equaling nRT. Remember, pressure is in atmospheres, volume is in liters, N is in moles, T is in Kelvin. So it gives us our volume, gives us our V, gives us a temperature, but we have to add 273 to it to get our true temperature, which we would get 296 Kelvin. And we have our moles, which is an N. Now, we're solving for pressure, so what we go ahead and we do here is we divide both sides by volume, and we get this equation. So when we plug it in, all we do is we have pressure equals our moles, which is 1.10 moles, times our ideal gas law constant that never changes, 0.0821, times our temperature of 296 Kelvin, all divided by a volume of 4.88 liters. Plug this in our calculator and we get a pressure in atmospheres of right around 5.4778 ATMs.